So I'm Nick DiVincenzo. I'm an application engineer with Siemens, focusing on our Simcenter Testing solutions. Just to start, we have an agenda for what we're going to cover today. Since reverberation time is dealing with sound and how sound decays, or the rate of decay of sound, we're going to briefly go over some sound basics, and then we'll jump into the meat of the presentation afterwards. So reverberation time, what is it? Why is it important or practical? Why do people care about it? There's two methods for calculating reverberation time that we'll discuss: the interrupted noise method and the integrated impulse response method. We'll talk about applications to calculating the sound absorption of materials, because that's one of the bigger applications of reverberation time, is in use for calculating sound absorption. And then we'll jump into how reverb time is calculated using Simcenter Testlab. Just to start off, let's talk about sound and what it actually is. Sound is our perception of pressure fluctuations which propagate through a specific elastic medium. So a gas, a liquid, or a solid. Maybe not, but there's this little tuning fork on the right-hand side. And basically this is exciting the air around the tuning fork, and then you can see a sound wave propagate through the air. So any vibrating surface that disturbs particles of the medium can act as a sound source. And the disturbed particles transfer momentum from one particle to another. In a sound wave, we have these regions of compression and rarefaction, so high pressure and low pressure. And that makes modeling sound as a sine wave a very convenient analytical tool. We've got some other animations here which I think really nicely express the idea that sound will travel even if there's no bulk flow in the medium. So here, if we just try and look at one of these red particle points here, we can see that there's no actual net bulk flow of the medium. It's this wave of high and low pressure that's actually traveling through the medium. In this case, let's say maybe that's air or some gas. Of course, there can be bulk flow. For example, if you're measuring sound in a wind tunnel, there's both the flow of the wind and then there's also the traveling of these pressure waves. And when we're analyzing a situation like that, we may need to account for that. But bulk flow is not necessary. When we're talking about reverberation time, it'll be very important to understand some of the differences between different acoustic fields. So we're going to introduce the concept of a free field here, where sound propagates without reflection and the sound level decreases with distance. Get my little laser pointer here, and we say my laser pointer is a microphone measuring the sound. This incident sound wave is only going to hit this microphone one time, and then it's going to continue to propagate to infinity. And in a free field, the general rule of thumb is for every doubling of distance that we move away from the sound source, we have a decrease in half of the sound pressure level. So in a free field, the big idea is the sound is propagating without reflection. And you may, in the course of your work or online, have seen these rooms called anechoic chambers, or maybe more commonly you might see a semi-anechoic chamber where this floor is concrete rather than these wedges. But the room consists of these wedges where maybe there's a sound source in the middle of this room. It's propagating out and it's being absorbed by these wedges, so the sound does not reflect back to whatever measurement microphone that you're using to collect your sound data. When we're talking about reverberation time, often the environment that we're going to be measuring in is a diffuse field. So in a diffuse field, there is a uniform sound field regardless of the microphone position. As the sound field builds up and stabilizes, if I put a microphone in this location, a microphone in this location, and a microphone in this location, they would all have the same sound pressure level reading. And you can see that we've got a source and these sound waves are bouncing and reflecting off the sides of this room, and that's kind of what's causing this buildup of, I'll call it, a reverberant environment. Most real life examples are somewhere between a free field and a diffuse field, but we'll often approximate different environments as a free field or a diffuse field. If you're in a concert hall, for example, that might be approximated as a diffuse field, or a parking garage as a diffuse field, as an example. And even some cab spaces within a vehicle, we, more or less say, okay, we're going to, for the purposes of our analysis, treat this as a diffuse field. When sound interacts with a barrier in our analysis, we're often trying to figure out ways to attenuate sound, to either get rid of it or to lower its level to make it less perceptible to the person who's using the product. So it's useful to think of what happens when sound interacts with the barrier. There's really three things that can happen. So the sound can reflect off the barrier. This is what was happening in that previous example of a reverberant room that we discussed. It can be absorbed by the barrier. So it basically passes through this edge of the barrier and then is absorbed, and that vibrational energy is converted to heat or some other energy source. Or it can be transmitted through the barrier into the next adjacent space. This is very important when we think of designing a cab space and maybe putting in some sound absorbing materials, so foams in a room or trim material in a vehicle. And we want to think about sound transmission when we're looking at things like mufflers or doors, walls, windows, or the dashboard of a vehicle, and so on. Now that we've gotten those basics out of the way, let's talk about what reverberation time is. In really basic terms, reverberation time is a measure of how long it takes a sound to decay. Think of standing in a big empty parking garage and yelling, "Echo," and hearing those echoes back at you and trying to count and see how long it takes those echoes to attenuate to where you cannot hear them anymore. Reverberation time is a measure of how long it takes a sound to decay in an environment. And like we said before, in a free field, that sound wave passes by, let's say, a microphone once and continues onwards. But in an environment with reflective surfaces, so this could be the cabin of a vehicle, a concert hall, a parking garage, etc., the sound wave is going to bounce off reflective surfaces and travel past that measurement microphone again. Eventually, the sound wave amplitude will decay until the sound is no longer discernible. And we calculate, or we can measure something called a reverberation time, which is a value that's normalized to a 60 dB drop in sound pressure. A T60 reverberation time denotes how long it takes a sound to drop 60 decibels. We can think of it maybe a little graphically here, where I have a sound wave. We're starting at some constant high level time, and then whatever's causing this sound wave shuts off, and we see some decay of that sound wave to the noise floor. The amount of time it takes for this sound wave to drop 60 dB is called the T60 time. And we can calculate other things like a T20 or a T30. T60 is really, it's just a useful way of normalizing to a specific value. Even if we don't have a 60 dB drop in our sound, it's easy to make comparisons to T60 times for a different environment, or as we'll talk about a little later, T60 times for different materials when we're calculating sound absorption. Reverberation time is a function of frequency. T60 time will vary as a function of frequency, and we often are looking at reverberation time in 1/3 octave bands. So in this plot here, I have time to decay in seconds plotted on the y-axis, and I have different 1/3 octave band center frequencies plotted on the x-axis. So you can see that it's not all uniform. There is a frequency dependency when we're calculating T60 times. How is reverberation time often used? It's most commonly a metric that is used to qualify the acoustics of a space, like an office space, for example. It's a very reverberant environment. It'll be louder and maybe it'll be harder to hear people communicating. Likewise, in a movie theater, you would want low T60 times. That's why they put big velvet curtains surrounding the walls of the movie theater. You don't want reverberations or echoes or reflections from the walls kind of distorting the audio of the film. Where reverberation time is also used very frequently is for calculating the sound absorption properties of a material. And that usually takes place in a specialized room called a reverberation chamber. So a reverberation chamber is a room that approximates a very diffuse field, so it's all very reflective surfaces. And we use that to calculate T60 times. And we can then use those T60 times to calculate how well a material sample that was placed in that room will absorb sound. So there's two primary methods for calculating T60 time, and we'll go into a little bit of detail on both of those methods now. I've got a little sample setup that I've built here just to kind of illustrate the procedure of calculating reverberation time. In this case, we're assuming that you're in a reverberation room, but you could also do this in the cab of a vehicle or a building. We have a measurement microphone, so we'll be able to collect some microphone data. We have a sound source. This sound source will play a broadband random noise output to build up a uniform, or as uniform as possible, sound field within this reverberation room. And then both of these are connected to a data acquisition system like our Scatus Mobile with a source output so it can drive this sound source. And then this is connected to a measurement PC. The way the measurement will go is we'll first build up the sound field. So we'll start the sound source and we'll build the sound level until it fills the area uniformly. And we call this the high level time. So that would be this portion of our little sound decay curve here. We'll make sure that we play this source long enough to build up a stable high level time. This usually is a couple of seconds. In my experience, maybe 3 to 5 seconds. Some folks will go a little longer just to ensure that the field is uniform and stable. And then once we are happy with this high level time, we will cut the sound source. So we'll switch it off. And then that sound level will start to decay in the room. In practice, when we're actually measuring this in Testlab and analyzing reverberation time in Testlab, we will wait for a 5 dB drop after this high level time just to ensure that we're not capturing any weird artifacts at the end of this high level time when we're measuring the slope. We want to make sure that we're only measuring the slope. And so the calculation of the reverberation time will begin after a 5 dB drop. And this is a parameter within Testlab. So if you wanted to change this parameter, the user would be able to do so. We continue measuring or analyzing or calculating the reverberation time along this slope until we get to a certain level above the noise floor of the measurement. Just like having this high level time, we don't want to include the noise floor in our calculation of the slope because it's going to skew the results. And so we specify a certain level above the noise floor. Default value is 10 dB to end the calculation. And so we end up measuring this whole signal, but we're only calculating the reverberation time from this 5 dB, I'll call it cutoff point, below the high level time down to this 10 dB value above the noise floor to try and make sure that we have good, clean data and measurements when we're performing the analysis. One thing to be very careful with when we're measuring reverberation time is noise on our data. Typically, in the real world, we're not going to have really nice decays that look like this for all frequency bands. Oftentimes, there might be a room mode, for example, and so you might see, we'll see how good I am at drawing here, you might see a little hook or ringing, something like that, at the tail end of your noise floor measurement. Oftentimes, when this is decaying, there might be a little hook up or knee up, and then it continues to go back down. It just, in practice, there's often noise on our data. We want our reverberation time measurement, these decays, to look as much like a linear slope as possible. And this example here on the left is maybe a more practical example of what a decay rate might look like in real life. This would be okay to analyze. If you have something that looks like this, or something with a extremely low drop or decay, so maybe it only drops from 60 dB to 50 dB, for example, so there's a really small drop in that sound pressure level, those will be very difficult to use to calculate reverberation time. So you might have to explore trying to improve the acoustic environment in that case, determining what exactly is causing these spikes in the data. For example, like on the previous slide, you might need to add diffusers into your reverberation room to get rid of those room mode locations, or you could also add some more microphones into that room to take more of a spatial average of the room when performing the measurement, and so on. But reverberation time really is a you get in what you get out type measurement. And if we don't have a decay rate that is somewhat smooth for analysis, it's very hard to calculate the reverberation time. I had previously covered the fact that we also need to make sure that we have an adequate decay range. But if we think about a T60 time, so we're looking at a 60 dB decay, we need, or it's desired to have, an extra 5 dB in headroom on the front of this measurement to make sure we've got a 5 dB drop after the source is cut off. And we want there to be a 10 dB separation between the noise floor and the end of our measurement. For a good T60 time calculation, we need 75 dB of separation from the high level time to the noise floor. And that's not always the easiest thing to achieve. And so oftentimes what we'll do rather than calculating a T60 time is we might calculate something called a T30 time, which is the time it takes for the source to drop 30 dB, or a T20 time, which is the time it takes for the sound wave to drop 20 dB. And then what we'll end up doing at the end is we'll multiply a T30 by a factor of 2 to get it back to our normalized T60 time. And our T20 we would multiply by a factor of 3 to get it back to our normalized T60 time. Just an illustration of what a T60 time, a T20 time, and a T30 time might look on this sample sound wave that we've been using. Here's my red extrapolated slope for my T60 time, or extrapolated is not maybe the best word here, but the calculated slope for my T60 time here. In a T30 time, we would use half of this amount of time to calculate this slope. And in a T20 time, we would use 1/3 of this to calculate the slope. But it's important to remember at the end of the day, we're multiplying this T30 time times 2, and we're multiplying this T20 time times 3 to get back to our normalized T60 value. So what this T30 and this T20 time are doing is they're just allowing us to calculate a T60 time for sounds that won't have this full 60 dB drop in whatever environment they're in. So that's the one method of calculating the T60 reverberation time of an environment. The other type is the integrated impulse response method, which is where rather than having a sound source that's building up a reverberant environment by playing something like a broadband random signal through a speaker, we have one sharp near instantaneous sound that produces some noise. So oftentimes folks will use a balloon popping or a gunshot type excitation, an explosion. And then we measure the decay using that as our excitation source. When using the integrated impulse response method, this sudden noise, it could be a door slam, a gunshot, many different types of excitations, it produces a distinct series of echoes, but there is only one sound wave. And so there's gaps in the measured sound pressure between when a wave is passing the microphone and when it's returning from another surface. It's not a pure reverberant room environment where everything is always uniform in the room because we've built up this perfect broadband excitation in the room. The solution for extracting a smooth decay from that single shockwave was designed by Schroeder, who applied an integration in the time domain of the squared sound pressure level. And this gave you a decay slope, typically with two components. So there's a slope here and a slope here. And this allowed you to calculate a T20 or a T30 time typically from this type of more explosive impulse type excitation. One of the primary drivers for calculating T60 time is for sound absorption, understanding how well a material will attenuate an incident sound wave. Like we talked about earlier, when a sound is hitting a barrier, three things can happen. It can be reflected, it can be absorbed, or it can be transmitted. If you're in a passenger car, let's say, for example, we don't necessarily want there to be echoes flying all around the vehicle. It'll make communication more difficult. It'll be annoying to the passengers. It'll be loud. And so there's trim or acoustic material all around the vehicle, which is working as absorbers to absorb incident sound. When you're designing this vehicle or you're designing these acoustic materials, depending on the type of work that you're doing, we want to understand how well the sound is attenuating noise. And we want to understand what frequencies it's good at attenuating and maybe what frequencies it's not doing a very good job of attenuating. We can calculate the absorption of materials as a function of frequency by comparing the T60 time of an empty room to the T60 time when we put a sample of that sound absorbent material in the same room. So we calculate the T60 time of an empty room, we put some absorbing material in the room, calculate the T60 time again, and we hope the T60 time is lower now that we've got this sound dampening material in the room that should be absorbing some of that sound wave. There's a number of different standards that specify these types of calculations. I've just spelled two of them out here. So ISO 354 and ASTM C423 are two standards for calculating the sound absorption properties of materials using reverberation rooms. So now we're going to walk through some of the practical considerations for calculating reverberation in Simcenter Testlab. A summary of what's needed in the software. As an input to this calculation, we need some time data. And as an output, we get a curve of reverberation time on the y-axis with octave center frequency on the x-axis. And we need a couple of add-ins. We need the ANSI-IEC octave filtering because this is done using octave filters in the time domain rather than through an FFT process. If you're processing this offline, we need signature throughput processing. And if you're measuring this online, so while connected to hardware and actually taking data, we need to have the source control active in order to use the interrupted noise method. So sending out a source to a speaker to build up a random environment in the noise chamber. I'd like to call out two properties that are very, very, very important when setting or calculating reverberation time, because these are both really the most important, I think, parameters to set here, and they're also the most difficult to set. So the first one is this time increment here that is set in the tracking and triggering section of either Testlab signature acquisition, or in this case, I'm showing the menu from signature throughput processing. And so this increment here is related to the number of data points that we analyze along the slope decay here and how far away they're spaced from each other. The distance between these data points in time is this increment. And a value I've used often, so I'm just including it in this presentation. This obviously will not work for all instances, is 62.5 milliseconds. And so this increment is very important because we want to make sure we are looking at enough points along this decay. So often in standards, it is called out that there's a specific number of points that might need to be specified along the decay to consider it a good curve. But if we've got a really noisy curve, if we have too many of these points, we might not get a good average decay if this increment is too fine, and likewise, if this increment is too wide or too large, we won't have enough points along the decay. So this increment specifies the distance between all these data points. The other very important parameter here are the time averaging parameters. The increment specifies where we're going to begin our analysis of the slope, and then these time averaging parameters specify how much data around that point are we going to use when we're calculating the sound pressure level. And so in Testlab, there's two different methods. It can be linear or exponential, and an averaging frame can be specified. Here I'm showing this as a linear frame. You can also choose exponential on this method. We can use the different values for a time constant that you might see in a sound level meter. So if you've used a sound level meter before, most of them have a fast, a slow, and an impulse method. So those are pre-configured in here, but the user can also specify an exponential averaging frame here as well. The increment defines where these points are centered along the decay curve. And then this averaging frame value specifies how much data we're actually using to calculate the average sound pressure level over this particular point. And these are the, in my opinion, the two parameters that are the most important when trying to calculate reverberation time, because setting these parameters incorrectly will result in an inaccurate measurement of this slope. Unfortunately, these parameters can be very difficult to determine. The reason for this is because they are very dependent on the rate of decay, and the rate of decay is also dependent on what frequency chunk that you're trying to analyze. For a really fast decay, we might want a very fast or very low increment in average size, which then maybe is suboptimal for a decay that's slightly slower. They also often require some pre-existing knowledge of the T60 time of the environment or the sample being tested, in that there's optimal combinations of increment and averaging frame depending on the decay rate. These things are always really challenging where we're testing something to try and determine the T60 time, but we don't know the T60 time, so how are we supposed to be able to calculate the correct parameters for calculating the T60 time? And often there's a little bit of almost guessing and checking that might be required, calculating these parameters with a couple of different frame and increment values until you get a stable result when you're going through and you're calculating T60 times for the first time. The best set of these parameters can also be influenced by noise and other room irregularities, like a mode in the room that you're using to test. And so this goes back to that data quality section where we have a really small averaging frame and there's a chunk of the room mode in that averaging frame, we're going to get an inaccurate value for the decay rate at that particular point along the slope. And then that's going to result in an erroneous slope calculation. So in that case, having a longer chunk or set of data would result in a more stable average, but it could have some impacts on other parts of the signal. So this increment and this averaging frame can be very difficult to select. You can also find some recommended starting points for calculating increment and averaging frame in different ISO and ASTM standards. Again, this is citing ASTM C423. The output interval shall be short enough to provide at least 5 measurement points per band. So this increment needs to be small enough to provide those 5 points. And the interval time, that's what they're stating with this integration time, shall be between 90 to 100% of the output interval time. And so by reading through these various standards, you can find maybe a good starting point for whatever material that you're testing. Now let's run through this calculation in Simcenter Testlab. So I'm in Testlab Signature Acquisition. I have under Tools Add-ins the ANSI IEC Octave Filtering add-in turned on. And then just so I can record the time histories, I also have time recording during signature testing on and source control. So if I go to channel setup, my little setup here is I just have a single channel turned on my SCADA's front end, and I'm actually just feeding the source directly into that particular channel, just as a simple example of how this would work in the software. So I've set up my acoustic channel, channel 1. If I go to tracking setup, I've set an increment of 62.5 milliseconds and a total measurement duration of 10 seconds. And in acquisition setup, I have some settings set for my source output. So you can see on output 1, I have it checked on. It's a random signal. And in this example, I'm outputting 1 volt from the source on the DAC and feeding that into my dynamic channel. So if I hit start source here, hopefully we'll see a big kind of kick on as I'm recording this on my dynamic channel. If I hit stop source, you'll see that decrease. I'll hop over to online processing, and when I turn on that octave filtering add-in, I get this real-time octaves section here. In real-time octaves, I can go to reverberation, and I can specify the octave band type I'd like, an upper and a lower center frequency for my calculation, and then I have these different time averaging parameters that I can set as well. I can choose my high level time, I can choose my decay start time, my distance to the noise floor, and my decay curve extrapolation type if I'd like, and I'll maybe do a T30 in this case. I'll hop over to measure, and I've got a sample display here with just showing a 1/3 octave section from the 1000 Hertz octave band center frequency. I'm going to hit ARM. I'm going to hit start, and then my front end is going to automatically have 3 seconds of high level time on the source, and then it's going to cut the source. It's going to measure 10 seconds because that's what I've specified in the software. And then this 1/3 octave section is going to be calculated. And then from the 1/3 octave section, the decay rate for this 1000 Hertz center frequency 1/3 octave band will be calculated. So here, if I look at my cursor, you can see that I had 3 seconds of high level time. Then my decay began, and eventually, after a couple of seconds here, it reached the noise floor. Let me disarm here. And one, I think, interesting piece of data that we give you when calculating reverberation time is you can look at the decay regression that is actually used to derive that T60 value. So if I go to the 1/3 octave 1000 Hertz regression here, I'll put that on top of my display. I can actually see, maybe make this a little wider. I can see essentially the section of the slope that was used for calculation of my reverberation time. And because it's specified a T30, this is 30 dB long. If it was a T60, this would be 60 dB and so on. And so this gives you just a nice, maybe data quality check, a nice warm and fuzzy feeling that you've calculated a good T60 time and that it's actually representing the decay accurately. I'll also briefly talk about calculating this offline. And so I have another Testlab project open here in the background. And here I've just got some throughput data, and I've plotted one of the microphone channels. So this is raw time data, and you can see that there's some buildup of sound or high level time sound here. Eventually that source gets cut off and that sound decays down to the noise floor. So I'm gonna take this, I'm gonna replace this in the input basket. I'll go to time data selection and hit replace. And here, depending on how long my time history was, I might want to choose a data processing segment to use. If I've got a lot of noise here measured at the very end of the signal, we're not actually using that for the calculation of the reverberation time. So as an option, you could set a smaller portion of either the high level time or this decay time to use for the calculation. In this case, because I'm not processing a whole lot of data, I'm just going to use the full 13 seconds. But if you've got a lot of data to process, it will speed it up by just selecting a shorter segment of this signal to use for processing. In time data processing, I will turn all my microphone channels on. Here in this particular measurement, there were 6 microphones in the room to get a better spatial average of the reverberation time. Under acquisition parameters, I've chosen my tracking parameters, so my duration and my increment. Under section, I can go to this reverberation tab, make sure calculate reverberation time is checked on, and then again, I can choose my octave band types for calculating reverberation time, my method, my averaging frame, and all these other parameters that we've looked at before. I'll hit close here. Let me call this TP2 is fine, and I'll select calculate. And now I'll hop back over to Navigator, and let's look at some of these results. So I've pre-plotted them. All of this data is in run 1 TP2. These are some plots from process data during this run. Here you can see, unlike what I showed you during the online processing, that your data is, I think, more likely to look like this occasionally rather than having a really nice smooth decay. So you see there's this little hook or this little knee in the data as it's decaying. And so here it can be really nice to have these regression curves because you can see exactly how this slope is being calculated, and you can make sure it's still an accurate slope calculation, even if there's some jumps or some hooks or some data that's not a perfect linear decay. You'll tend to see this behavior more in lower frequency data. So this is looking at the 100 Hertz 1/3 octave section. If I look at a higher frequency 1/3 octave section, this is 1000 Hertz from this data set, you'll see that the slope is a lot nicer. So behavior like this is more likely to occur when you're looking at those low frequency 1/3 octave sections. And then finally, I can go over to an octave plot, and let me actually plot my reverb time data here. And you can actually see for one of these microphones what a real reverb time plot might look like. Okay. Thank you, everyone.